Welcome to this video. This video is to teach you what is meant by standard electrode potential of a certain metal and to compare with a certain reference. Well, why we want to know about the standard electrode potential? Well, standard electrode potential itself means the tendency of losing electrons. So if we know the standard electrode potential more clearly, then we can compare which metal or which chemical species can actually lose electrons more readily, and then we can suggest or predict whether a chemical redox reaction will occur. So by doing this, we're trying to measure the standard electrode potential in a very standard condition. So the conditions are standardized to be 1 mole per dm cube of that particular iron solution, okay, and the metal should be immersed into that particular solution, and then in a temperature of 298 K or 25 degrees Celsius. So this is the standard electrode potential about. So let's say, for example, if I want to know the standard electrode potential of iron, that means iron, it can lose electrons into Fe2 plus 2 electrons, or in reverse, actually it can be accepting electrons, Fe2 plus 2 electrons, and then turn into Fe metal. So if we want to measure this one, then we have to prepare an electrode of iron metal, and then we immersed it into a beaker of solution of 1 molar of iron 2 maybe sulfates solution, okay. The anion itself does not matter, okay, and then the temperature is 298 K and then 1 atm, okay, and then that's it. So this is the standard electrode of iron metal, okay. So it is ready to compare, but problem comes, what should we compare? We should compare with the simplest atom in the world, okay, which is hydrogen. So we have to compare with hydrogen this time. So we have to prepare the standard electrode of hydrogen. Hydrogen itself, hydrogen ion, can actually accept 2 electrons and then become hydrogen gas. Or on the other hand, hydrogen gas can actually can lose electrons and become hydrogen ion, and like this. So in order to perform this, then we have to prepare a tube that input the hydrogen gas with 1 atm, okay, which is a standard condition in the world, okay, and measured at 298 K like what we've mentioned, okay. Well, we have to use an inert electrode, okay. So the inert electrode this time we use platinum, okay. It's inert enough because it will not react with hydrogen gas and it will not corrode that easily, okay. And then we have to immerse it into a solution of containing hydrogen ion. But problem comes, what is the hydrogen ion containing solution that we have to use? Okay, then commonly we can use hydrochloric acid. Hydrochloric acid itself is a strong acid, that means it can dissociate completely into hydrogen ion and chloride ion. Okay, well, besides hydrochloric acid, we can also use nitric acid. Nitric acid serves the same purpose as well. But how about sulfuric acid? Can we use 0.5 molar of sulfuric acid to dissociate enough amount of hydrogen ion and to measure the standard electrode? Well, for this case, no. Okay, because sulfuric acid itself, the double dissociate, because it is a dibasic acid, when it dissociates the first time, it is a complete dissociation. However, for the second time of dissociation, that means dissociating from hydrogen sulfate into hydrogen ion and sulfate ion, this dissociation is not complete. So we cannot count this one as a complete dissociation, and then we put 0.5 molar of sulfuric acid and pretend it can give out 1 molar of hydrogen ion. Okay, not to mention other weak acid like ethanoic acid. Even though you got 1.0 molar of ethanoic acid, it's not going to happen to have 1 molar of hydrogen ion. So that's why the common one would be the commonly used hydrogen ion provider will be hydrochloric acid or nitric acid. So in order to compare our own half cell and the standard electrode, okay, we have to connect them together. So we have, say for example, this time I want to measure zinc metal, so I immerse zinc into zinc ion containing solution of 1 molar, say for example zinc sulfate solution, okay, and then we use zinc metal as the electrode. Connect with the other side connected to the hydrogen standard cell. Okay, so this is the hydrogen standard cell. Oh, beautiful color. Okay, so this hydrogen standard cell, okay, connected together with a salt bridge. Salt bridge, like what we have mentioned or we have learned in IGCSE, the salt bridge can use potassium nitrate as a typical electrolyte. Okay, immerse or actually you soak the filter paper with potassium nitrate solution, then this one could be the salt bridge. And then we connect it to a high resistance voltmeter. Okay, why we use a high resistance voltmeter? Simply we want a more accurate result. And then the hydrogen standard electrode will connect to the negative terminal of the voltmeter, and then it will the positive terminal will be connected to our own sample. So by doing this, then we hydrogen standard electrode will have a voltage of 0.00 volts. Okay, so when we measure this, okay, have the reading, we will notice that actually zinc can give you minus 0.76 volts. Okay, why this one should be a negative value? Okay, simply because in this case, zinc actually loses electrons. Okay, so zinc loses electrons, pushing electrons towards the positive terminal of the voltmeter. That's why the voltmeter reading will become a negative value. So by doing this, we can actually notice we can actually prioritize a lot of different metals and different different solutions. Okay, and in order to know the electrical potential. Okay, the following is actually the electrical potential table cropped it from the LSL IGC International A-Level Data Handbook. You can notice that for sodium metal, it loses when it undergo a certain and we try to measure the electrical potential itself. Okay, it has a very negative value, which means sodium actually loses electrons very, very quickly. Okay, and the tendency of losing electrons is very, very high. So we can conclude that the more negative value we have, that means the species should lose electrons readily. Okay, if it loses electrons readily, that means it should be a strong reducing agent. Okay, and on the other hand, okay, and another thing that I want you to notice would be the hydrogen itself. Hydrogen itself is located here. Hydrogen itself is located here, okay, and it has a voltage of 0.00 volts. Okay, so this is why where we put our reference in. And on the other hand, okay, besides the after looking at the very negative value, then we'll start to look at the very positive value. Okay, the more positive value, that means okay, these permanganate ion is very famous that it is a very, very strong oxidizing agent. Okay, so we can come to a little bit of conclusion that the more positive the value, that means it gains electrons more readily. If that's the case, That means it is a stronger oxidizing agent. So when you come to this point, you start to think about, oh, what about we put sodium metal and permanganate ion together and form a chemical cell? Then we can generate a very, very huge amount of energy, like positive 1.51 plus for sodium is negative 2.71. That means it can generate a voltage of 4.22. Wow, then this is amazing. Okay, if we can generate this much of power, then definitely it will be a very, very nice battery, right? Okay, but we have to think about it. Sodium metal itself, although it can generate a high voltage, but it can be loose. The metal can degrade or diminish or even disappear in a very, very short period of time. Even though the voltage itself is very high, but it is not long lasting. So that's why when we are designing a battery, we not only looking at the voltage itself, but also look at how long the service life it could be. But this one definitely opened the door for us to know more about how to design a battery or design a chemical cell so that it could be more long lasting, okay, but and generate enough amount of energy for us. So in the next video, we will learn more about how to make use of this table and calculate the voltage, or we try to know whether the chemical reaction is feasible or not. Thank you for watching.